Hi, my name is Travis White. My partner is Ben McDaniel. For our project, we decided to develop and construct a solar oven and measure its steady state temperature. So our experiment included constructing an oven and developing a mathematical model to describe the steady state temperature for single pane glass, so we can predict what it's going to be, and then we wanted to test the actual steady state temperature and compare it to what we predicted. Along with that, we wanted to see how it changed over time, just so we know how long it takes to hit that temperature to best prepare for cooking.
So to start constructing our solar oven, we got a wooden box to serve as the inside of the oven. Then we had connected 4 mirrors that we could adjust the angle on. And then we covered the box in an insulation foam and then surrounded it all on cardboard. And then we had a nice glass lid. We also attached a thermocouple to measure the temperature of the inside of the box. We also measured the temperature of the glass so that we could use it as a double check to make sure that we were calculating the correct temperature. So some of the other things that we considered as we designed it was we painted the inside of the box black to absorb a larger amount of radiation. It also simplified our equations because we could assume black body radiation. The 4 mirrors, we used a laser light and a flashlight to make sure that we were directing the maximum amount of sunlight into the box to decrease the time that it took to cook. Then the insulation on the sides and the bottom let us ignore the effects of conduction and convection. We knew they'd be very small.
Our model, we had to make certain assumptions to simplify our equations. We assumed isothermal glass. We assumed that the surface temperature of the box was the same as the temperature of the air inside of the box. Also that the cavity of the box behaves as a black body. The solar spectral distribution was a black body, and we neglected forced convection on the outside of the glass. We tried to do our testing in non-windy conditions to exclude forced convection. So our main equations were our energy balances. The first one you see is an overall energy balance where we include the solar irradiation of the sky and then of the sun, and then we have the convection, free convection on the outside of the glass box, of the glass part of the box, and then we have our free convection on the inside, and then we have QS, which is the energy being radiated from the box out of the box or out of the system, and then you have your radiation from the glass. And then our next equation is an energy balance of just the pane of glass, where you have your convection on the inside, and then you have your solar irradiation, and then you have your energy from your box into that glass. So our supporting equation is our QS, or the energy from the box. And with that, we had to use our shape factor. So we have the area of the surface of the box times by the area of the surface into your glass surface. And we know that from the reciprocity relationship that your AS FSG is equal to AG FGS. And we know that all of the light and energy is going through the glass into the surface. We know that's equal to 1. So when you put that into the equation, you know that the area of the glass is equal to your AS FSG. And then you can put that into your QS, and then as you put QS into your main equations, it allows for you to cancel out all the other areas of the glass in each of these terms. We also used forced convection, so we used this we used free convection, so we used this Nusselt correlation to be able to solve for the heat convection in each of the convection terms. So these were our data. We used a solar irradiation that we found on Weather Underground, which was on average about 750 for the time period that we were doing our testing. We approximated atmospheric emission at 230 Kelvin. And our model predicted that the temperature of the glass should be 95 degrees Celsius, and the temperature of the box should be about 156 degrees Celsius. After 80 minutes, we were able to measure the temperature of the glass to be 105 degrees Celsius and the temperature of the box to be 152 degrees Celsius. And you can see from our chart that we were hitting steady state, we were leveling out, and our temperature wasn't changing anymore at about the 80 degree mark.
So after the experiment was performed, we looked at some possible ways to improve the solar oven if you ever wanted to build one. So one thing that is definitely helpful is to use double pane glass for your lid, because it allows for an extra dose of the greenhouse effect and helps keep some of the radiation inside the box and also prevents some of the heat loss from convection. You could also make some improvements to the insulation, maybe use something thicker around the outside of the box, and then to really make sure that you're not letting any heat escape from where the glass lid meets the box. And then the last thing would be to increase the size of the mirrors or your reflective surfaces to help get to your maximum temperature more quickly. And so our conclusion was that you can build an effective solar oven for not very much, and it doesn't take very long, and that you can approximate what your maximum temperature is going to be using these equations. And our percentage error for the temperature inside the box was about 2.6%, and we were also pretty confident in our temperature for the predicted glass, and that allows us to be pretty confident in our conclusion.